In this video, we're continuing our discussion of ordinary differential equations. And in particular, we're going to talk about solving systems of initial value problems. So many engineering problems contain systems of initial value problems, in which more than one dependent variable is a function of one independent variable, for example, time. So for example, chemical reactions of more than one component are usually described using systems of initial value problems, in which the initial conditions are known. Similarly, the interaction of biological growth of different species, such as the predator-prey model, is usually represented by a system of initial value problems in which the initial conditions are given. Generally, these systems can be represented as shown here. So for example, dx1 by dt is equal to a function of x1, x2 up to xn as well as time. And then we can have a second equation, dx2 by dt is equal to a function of x1, x2 up to xn as well as time. And we can have up to n of these equations. dxn by dt is equal to some function fn of x1, x2 up to xn and time. The independent variable is discretized such that t0 is less than t1, which is less than t2, etc., up to tm, with a constant step of h is equal to ti plus 1 minus ti. In such systems, the initial conditions are given, which are the values of our dependent variables x1, x2, x3 up to xn at some given time t0. And then the values of x1, x2, xn at the next time step. So for example, when t is equal to ti are denoted as shown here, where this I is shown in the superscript. In this case, the values of the dependent variables at t equals ti plus 1 can be obtained using the following system of equations. So x1 at I plus 1 is equal to x1 at I plus some function phi of h. And then up down to xn at I plus 1 is equal to xn at I plus some function phi n of h, where these phi's depend on the method used. So for example, if the explicit Euler method is used, then the phi's, phi 1 through phi n, are given as shown here. So the functions are functions of x1, x2 up to xn and t, all evaluated at the step I. For the classical Runge-Kutta method, then the phi's take the form shown here, where they're this functions of these k's 1 over 6 k11 plus k plus 2 k12 plus 2 k13 plus k14, for example, down to 1 over 6 times kn1 plus 2 kn2 plus 2 kn3 plus kn4, where these k's are the k values associated with the dependent variable xj. And they're given in the classical Runge-Kutta formulation. It should also be noted that higher order initial value problems can be solved by converting them into a system of multiple first order initial value problems. So for example, if we have an initial value problem that has, which is second order, so it has a second derivative, such as d2x by dt squared is equal to some function of x and t, and if the initial conditions are x at 0 and x prime at 0, or the dx dt at 0, then we can convert this into two first order initial value problems. So we can do this by setting another variable y equal to dx dt, and then the equation can be written as a system of two first order initial value problems. So dx dt is equal to y, and then dy dt is equal to f of x and t. So basically, if we put in here our dx dt for y, and then we take the derivative again, we can see that what we get is d2x by dt squared is equal to f of x and t, which is consistent with our initial problem. And here then the initial conditions would be given in terms of x and y, where again y was equal to the derivative of x with respect to time. So let's look at an example. Let's consider the damped spring mass system with m is equal to 1, k is equal to 1, and c is equal to 0.5. So we know that this system follows the second order differential equation shown here. So m d2x by dt squared plus c dx dt plus kx is equal to 0, which describes the free vibration response of this damped spring mass system. And here, with m is equal to 1, k is equal to 1, and c is equal to 0.5, we have this form of our differential equation. So with initial conditions at time 0 of x is equal to minus 10 and x prime is equal to 0, we can solve this system. So basically the system is displaced to x is equal to minus 10 and then released from rest, and we can find the response as the position of the mass over time. So to do this, we want to use the numerical, we want to find the numerical solution for the position and the velocity for t from 0 to 20 seconds using the explicit Euler method as well as the Runge-Kutta method, and using a step size of h equals 0.1 for both methods. So the differential equation is given as the second order differential equation shown here. The exact solution can be obtained analytically, and the exact solution for both the position and the velocity are shown here, where this x prime of t represents the velocity. So we can notice that this is a second order ODE. So this means that we can convert this into a system of two first order initial value problems. So if we set y is equal to dx dt, then the equation can be converted into the following system. So if dx dt is equal to y, dy by dt is equal to minus 0.15y minus x. With our initial conditions, x of 0 is equal to minus 10 and y of 0 is equal to 0. So basically to get this equation here, we have moved these terms to the right-hand side, and then we set y is equal to dx dt, and then we take the derivative of y with respect to t, we get d2x by dt squared, which is this function of x and t here. So with h is equal to 0.1, the interval is split into 200 time steps. So the time discretization is such that we have t0 is equal to 0, t1 is 0.1, t2 is 0.2, up to t200 is equal to 20. And the corresponding positions are given by x0, x1, x2, up to x200. And the corresponding velocities are similarly denoted with y0, y1, y2, up to y200. So using the explicit Euler method, the values of xi plus 1 and yi plus 1 can be evaluated using the expression shown here. So xi plus 1 is equal to xi plus h times dx dt evaluated at the stuff that we already know. So xi, yi, and ti. So in this case, xi plus 1 is equal to xi plus h times yi. And now yi plus 1 is equal to yi plus h times dy by dt evaluated at the stuff that we know, which is xi, yi, and ti. So in this case, our dy by dt, we can plug that in here. So our yi plus 1 is equal to yi plus h times minus 0.15 yi minus xi. With our initial conditions, x0 is equal to minus 10, and xy is equal to 0, we can calculate the values of x1 and y1, which are basically the values at time t1 is equal to 0.1. So x1 is equal to x0 plus h y0. So plugging in our values, we get that x1 is equal to minus 10. y1 is equal to y0 plus h times minus 0.15 y0 minus x0. So plugging in our values, we see that y1 is equal to 1. Similarly, we can calculate the values for x2 and y2. So x2 is equal to x1 plus h times y1. So plugging in our values, we see that x2 is equal to minus 9.9. y2 is equal to y1 plus h times minus 0.15 y1 minus x1. Plugging in our values, we see that y2 is equal to 1.985. And we can continue on to find the values of position and velocity at each time step. And this is the output from this procedure implemented in MATLAB. So using the explicit Euler method with h is equal to 0.1, these are the results for x and y for the first 3 seconds, and you can see in the plot it goes up to 20 seconds. And you can see the explicit Euler approximation shown in the black dots and the exact function shown in blue. And you can see that with this time step, it does not provide a great estimate of the actual position or velocity. So the effect, we can see the effect of the step size. If we decrease the step size, we get a much better approximation of the exact solution. So here we're using a step size of h is equal to 0.1, and here we're using a step size h is equal to 0.01. And you can see that we're almost overlapping the exact solution. You can see there's a little bit of differences in these areas of high variation. And if you recall that the explicit Euler method has a fairly small stability region, which means that if h gets bigger, we can run into these issues with numerical stability where the solution will just continue to grow as time increases. And so you can see with even an h of just 0.3 that the explicit Euler solution for this problem begins to grow in an uncontrolled manner. Now we can solve the same problem using the classical Runge-Kutta method. So here again, we've split our second order ODE into 2 first order ODEs. So f1 of x, y, and t is dx dt is equal to y, and f2, which is dy dt, is equal to minus 0.15 y minus x. So using the classical Runge-Kutta method, the values of xi plus 1 and yi plus 1 are evaluated as these linear combination of our k values as shown here. So these ones for the first function for our f1 are denoted k11, k12, k13, and k14. For our f2 function, they're denoted k21, k22, k23, and k24. Where these k's are defined here. So k11 is our f1 evaluated at xi, yi, and ti. So that was just equal to yi. Our k21 is our second function, f2, evaluated at the same points xi, yi, ti. So that's minus 0.15 yi minus xi. Then our k12 is our first function evaluated at our intermediate point. So xi plus h over 2 times k11. So this goes into here. And then yi plus h over 2 k21. So this goes into here. Plus ti plus h over 2. Then k22 is now our second function evaluated at the same points. So our k11, we've got xi plus h over 2 times k11, yi plus h over 2 times k21, and then ti plus h over 2. And then when you plug everything in, we get this expression here. Now k13 is our first function. So you see the first superscript or subscript corresponds to the first function, evaluated at our next intermediate point, which is xi plus h over 2 times k12. So now this goes into here. And then yi plus h over 2 k22. So this goes into here. Plus ti plus h over 2. And then our k23 is, the 2 here indicates the second function, and then the 3 indicates that it's evaluated at the same intermediate point, so xi plus h over 2 k12, yi plus h over 2 k22, plus ti plus h over 2. And then lastly, we've got our k14 is our first function evaluated at our last point, so xi plus h times k13. So we take this, it goes into here, yi plus h k23, so this goes into here, and then ti plus h. And then similarly for k24, the 2 indicates the second function, and then it's evaluated at exactly the same as the 4 above here. So if you recall that we're kind of subbing these in at each step so that the Runge-Kutta method requires this sequential evaluation. So plugging in our initial conditions, x0 is equal to minus 10, y0 is equal to 0, and h is equal to 0.1, into the k's in the previous slide, we get these values shown here. And when you're evaluating the method, you need to do it in this order because of this kind of sequential subbing values in. So we get our k11 and then our k21, and then you can see k12 relies on k21, and then k22 also relies on k21 as well as k11, and similarly as we go down. So you can see that we get all of these values. Then we can calculate our estimates for x and y at our next time point. So x1 is equal to x0 plus h over 6 times all of these k's. So k11 plus 2k12 plus 2k13 plus k14. So plugging in all of the values that we just calculated, and again h is equal to 0.1 in this case, we find that x1 is equal to minus 9.9503. Similarly for y1 is equal to y0 plus h over 6 times now k21, k22, or plus 2, k22, plus 2, k23, plus k24. Plugging in all of those values, and again h is equal to 0.1 and y0 is equal to 0, we can find that y1 is equal to 0.990883. And we can proceed to find the values of the position and velocity at each time step. And this is the output from the MATLAB code. So here shows our time, or at each time our x and our y for the first 3 seconds, and then the plots show the values up to 20 seconds. And you can see that for both this is the position and this is the velocity, with h equals 0.1, you can see that we get an excellent estimate of the exact solution using the classical Runge-Kutta method. And comparing this method with the explicit Euler method, this method here is 4th order accurate, so it's the order h to the power 4, whereas the explicit Euler method is just order h. And you can see here that it provides a much more accurate solution, giving the same time step. And you can see even with a much larger time step, h is equal to 0.5, we still get an excellent estimate of our exact solution at all of our time points. So this section was meant to show how we can use the methods for solving initial value problems to solve systems of initial value problems, and how we can also convert higher order initial value problems into systems of first order IVPs to use the methods that we've talked about to solve them.